Hey guys, this is the second attempt at the Chebyshev's theorem recording because the first time the sound wasn't being recorded. Okay, so we're gonna talk about Chebyshev's theorem right now, and so in the previous video you learned about standard deviation and variances and saw some numerical problems based on those. Okay, so Chebyshev's theorem gives you an idea about the distribution, right? And it talks about how to interpret things. So it tells you the minimum amount of people or proportions of observations that lies within plus or minus one standard deviation or two standard deviation. So the rule itself is this one. It's like 1 minus 1 by a squared. So here the example is this company has the average profit sharing per week amount is $51. And the standard deviation is 7.51. And so the question is at least what percentage of contributions lie within plus or minus 3.5 standard deviations. So here K is 3.5. And when you apply that, it's like 0.92. So this means 92% of the employees over here are within plus or minus 51.94. Okay, so that's the idea of the Chebyshev's theorem. So if you try and look at the idea of like this normal distribution, this is a normal empirical rule, and this Chebyshev's theorem you could kind of extend it. And so this is perfectly symmetrical, and within one standard deviation of the mean, so here the mean is 100. Within one standard deviation, you have 68% of the observations or population or people who fall within one standard deviation, which is here standard deviation is 10, which is between 90 and 110. And within two standard deviations, you get 95% of the people. And within three standard deviations, you pretty much get 99.7% of the people or the observations. And anything outside within three standard deviations is roughly considered as an outlier. And the good thing about Chebyshev's theorem over here is it can be done for any shape. Okay, it doesn't have to be symmetrical. It could be right skewed, left skewed, it could be uniform, it doesn't matter. No matter what you do, you apply this rule, that's the minimum number of observations which are present within that many standard deviations. Okay, so if in case you're interested in those things, so the problems in some sense are fairly straightforward and can be applied to. Okay, so let's try and look at another example. Okay, so I already wrote down certain things over here because I recorded this video once before and the sound wasn't being recorded. Okay, so let's take an example of another distribution. So this is a distribution of like income in India. Okay, so the average income in India is around $10,000 with the standard deviation being $4,000. Okay. And so if you try and think about, this is the percentage of our density in the y-axis, and the x-axis is income. So at the very bottom, you have extremely poor, and then you have some poor people, and then you have a bunch of middle class, and a bunch of like lower middle class, upper middle class, rich, and then rich people, and then you have like the ultra rich and billionaires and these extreme tail distributions. Okay, so this distribution is not very normal. It's not at all normal. But even here, if you want to try and think about, well, what percentage of population lies within two standard deviations? Here you could think about like so plus or minus two standard deviations would be 1 minus 1 by k squared is at least 75%. So it's at least 75% of the people in India earn between $2,000 and $18,000. Okay, so that gives you an idea of what the distribution, at least what percent of population is there. Okay, so that's where Chebyshev's theorem can be used in even different distributions. So the next topic is the idea of, honestly, these questions are very straightforward. If you just try and get one or two questions, just practice them either through the learning assignment or just go and take one or two exercise questions and do. So the next thing is the idea of relative dispersion rather than absolute dispersion. So when you talk about absolute dispersion, we primarily focused on standard deviations and variance. We also talked about mean absolute deviation, range, but whenever you have different units of standard deviation, it's hard to compare. It's hard to compare two different distributions, right? For example, here we have two distributions. One is the amount of money paid to the bonus paid per week for the year, and the standard deviation is given. And the other one is the years of service, which is 20 years, and standard deviation is around 2 years. Okay? So here, this coefficient of variation is just taking the standard deviation. S refers to the sample standard deviation, and you're dividing it by the X, which is like the mean in some sense. Okay, so that kind of standardizes and makes different distributions. Since you're dividing the standard deviation by the mean, this should be like X bar. Okay, so it's not really X. So think of it as X bar, which is the mean. So here the right formula is given, example, but whereas here it's not, the bar is missing over there. So once you're dividing it by the mean, you can compare apples to apples. So once you compare, and just the 100 multiplication is just to convert things into a percentage. So if you think the money distribution, the bonus distribution is 20%, and the coefficient of variation for the years of service is only 10%. Okay, so so the distribution is like way more, it's way wider. There's more variation in terms of like the bonus paid rather than the number of employees with different years of service, right? So here, 20 years of service, only small standard deviation of 2 years. That means most of the employees are around 45 years of age. There's not too many old people in terms of like 55, 60s, and there's not too many young people in their 20s as well. So that's the coefficient of variation, only used for whenever you're trying to compare different distributions to see which one is more narrow and which one's more diverse. And that's, again, straightforward. Like this, not too many variations of this. No. And the next topic is the idea of skewness, which we kind of talked about already. So let's look at this, these shapes. So this is like the perfect symmetric distribution, which is your normal distribution. And then you have your positively skewed, or the positively skewed is also known as like right skewed. And the negatively skewed is known as the left skewed. So positively skewed salaries, income is typically a good example. And for negatively skewed, test scores is a very good example, because we have very few students who are getting less than 30 or 40, right? Like even if you fail, you get like 45 for the most part. Unless you're doing PhD in math, and suddenly you take one PhD math course and you get lower than 40, let's say that. Okay, and bimodal distribution is another common example. Sometimes in grades you get bimodal distributions, a very difficult exam, and suddenly you get like a bunch of students who figure that out, the difficult questions, and they get 90s, and the others cannot figure that out at all, and they do not get any partial grades, and suddenly they'll all be in like the 50s. And you get like 2 peaks in your distribution. Sometimes it's not uncommon to see that. Okay, so in terms of how symmetric or how close is the distribution to being symmetric, if that's a question which you want to answer, or how skewed is the distribution? Is it really skewed, or is it only mildly skewed? Is it mildly negatively skewed? So these are some things which people would want. Like, for example, monthly salaries, the positive skewed, you don't want an extreme positive skewness, because that means a lot of people who are earning absurd amounts of salaries compared to the median and mean incomes, right? Like, and so you would want policy laws to take for that. So one way to try and figure out the skewness is using this Pearson's coefficient of skewness, where you're subtracting the median from the mean, and you're dividing it by the standard deviation. This dividing by the standard deviation is a concept of known as standardization, and it's mainly to like compare apples to apples kind of idea, rather than like so that you can make good comparisons between different kinds of distributions. Another way to compare to find out the skewness is by this formula, if you're trying to. So this is a lot closer to your standard deviation and your variance formula. If you recollect the formula for variance, the variance would have something x minus x bar divided by n instead of standard deviation, and it'll be to the power square. Okay, and whereas skewness is like instead of an n, like you're kind of accounting for the n, and then here you're dividing by the standard deviation, but this is a cubed. Okay, so for variance will always be positive, whereas skewness can be positive or negative because this is a cubed. Okay, so if x minus x bar is negative, this whole term will be negative. And if x minus x bar is positive, this whole term will be positive, right? So even you can even see from the graph, more observations on average, and the summation. This is also inclusive of the summation. Even in this Pearson's coefficient of skewness, x bar minus median, if the mean is greater than the median, so here the mean is greater than the median, that means it's positively skewed. If the mean is less than the median, it's negatively skewed. So the same idea applies in this formula as well as here. And so here's an example. The easiest way to try and here's an example to try and calculate both methods of skewness, and they're not that far off. So for example, the Pearson's method of skewness is 1, and the normal computation is 0.97. And if you do a graph for that, it kind of shows up nicely like this. Okay, and you could do your histograms, and like you could add a curve on top, and this is like mildly positively skewed. It's not ridiculous. If you have like values of like skewness of like 3 plus 5, that means the skewness is like a lot more. That means it's a lot more skewed. So depending on how far away it is from 0, the greater it is, the greater the skewness. And if it's positive, this is a positively skewed. If it's negative, it's a negatively skewed. Okay, so that's the idea of skewness. Again, don't be worried about these bunch of like formulas. Just grow comfortable with computing them either by hand in tables or via Excel forming things. And make sure you practice those calculations a couple of times just to make sure you're not missing any brackets, or like you're not multiplying 2 digits before it's supposed to be multiplied. And make sure you're dividing inside the brackets rather than outside the bracket, and so on. So you make mistakes and you learn from those mistakes, but the more you practice before, the less likely you are to make those mistakes. Okay, so then the last topic for this class is the idea of percentiles. Okay, so percentiles is the idea where it's like rank. You're trying to figure out the rank of each person or where the observation is before. Okay, so here there's different versions of like these measures include quartiles, deciles, and so on. So, okay, so if you let's think about this distribution over here. So think of this as your grades distribution, and like the mean is being 85 here. The mean is 85, and the standard deviation, so the maximum grade is like 100, and the minimum grade is 30. Okay, so the 75th, if the 75th percentile is equal to 85, that means, and if you scored 85 over here, that means you're greater than 75%. Your mark is greater than 75% of the people, if 85 corresponds to the 75th percentile. These things are used very commonly in GRE and SAT and other GMAT, any standardized exams. I think LSAT and like your med school exams. I don't know what it's called, MCAT, I guess. All these standardized exams. GMAT is used for MBAs, GRE as well sometimes. When I had to come to Canada to apply for grad school, I had my GRE score, and it would give you some sort of percentile based on your grades, right? So GRE scores were weird. Like I think they're out of 300. When I wrote, they were out of 800. I don't know. The scaling system is weird. So the grades are not that important. What's important is the rank. Okay, so if you're the 100th percentile, that means you're rank number 1. If you take any random 100 people, roughly, you're expected to have the highest grade. And if you're the first percentile, that means you're at the bottom of the barrel, right? You're the last rank. You're the last in grade. So here, the person who scored 30th is the 100th percentile. Person is the 100th percentile, and the person who scored 100 is like, sorry, the person who scored 30 is the first percentile, and the last rank is the person who scored 100 is the 100th percentile and the first rank. Okay. And this is the idea of a percentile. And the way you could kind of compute that is through this formula over here. Position, if you want to find out the 75th percentile, P is 75. N is the number of observations. If you want to find out the 25th percentile, 33rd percentile, 48th percentile, whatever it is, whatever you're interested in, that's P. Okay. So to try and give you another example, your textbook has some examples on, like, there's a bunch of commissions. The easiest way to try and do this is like to arrange in ascending order. So lowest commission to the highest commission. And remember, when P is 50, that's the 50th percentile. That's the same as your median. Okay, so when P is 50, that's the same as your median. And so the 25th percentile, if you want to find that out, P is 25. There are 20 observations here. That's your 5.25. That means you would locate the fifth value and then move 0.25 of the distance between the fifth and sixth values and report that as your first quartile. That's the value of your first quartile. Okay, so that's how you interpret this 5.25. So now let's go to another example as well. So what if you have like observations in terms of incomes, right? In Canada, we have like 25 million people. Population of Canada. Not population of Canada. Population of Canada for earning. The rest are like retired or children. So there are 25 million laborers or workers in Canada. And like if you want to try and find out the income, right? Let's say the government wants to try and introduce a policy where they increase taxes on the top 5% of the earners, top 5 percentile of the earners. This, if you want to try and do that kind of idea, you would want to try and figure out what is the 95th percentile? What is the 95th percentile? Is what you're interested in. And so to try and find out the location of the 95th percentile, you try and have n plus 1, P is 95. You divide that and you get a value of 23,750,000. That means you arrange all the incomes. Let's say the lowest income over here is $5,000. Person earning the lowest income. Anyone who earns less than $5,000, let's say they're not counted in our sample. They're counted as like small jobs, or so $5,000 is counted as like full-time worker or at least part-time worker. You're like that. $5,000 is the lowest income, and let's say the highest income someone earned in a year is $1 billion. Okay, and let's think about this 95th percentile, right? So 95th percentile will be like once you arrange all the incomes, right, in ascending order, 5,000, 6,000, 7,000, and you have a bunch of people who are making like the average salary, the median salary of like around 55,000. So that'll be like the 50th percentile. So that's the median value. And as you keep going, maybe let's say the 95th percentile, right? So it'll be around, after you count 23,750,000, 23,750,000 salaries, you kind of arrive at some value. Let's say that value is approximately $250,000. Okay, so if you earn $250,000, that means you're earning a higher income than 95% of Canadians. Okay, so that's the 95th percentile value, and you could kind of use this as a cutoff. Hey, anyone who earns over $250,000, the taxes go up by like 2%, or on all salaries greater than $250,000. Because this is the concept of marginal taxation, right? It's not average taxation, and some people get the idea of taxation wrong, but that's for another day and for another class. So this is the idea of percentile. So we covered dispersion, Chebyshev's theorem, percentiles, and the idea of skewness. And tomorrow we could work a few questions on a few exercise problems from these chapters and move on to probability. Right, I'll see you all in class.